Today, we're going to be reviewing a concept that we talked about in Chapter 8, which is all about similarity. We're going to specifically be focusing on similar polygons. So in this case, we're going to look at what it means to have these two triangles, ABC and DEF, be similar. There's two characteristics that you have when you have similar polygons. One characteristic is that the ratio of the corresponding sides are equal, and the second is that corresponding angles are congruent. So in this example, I'm telling us that these triangles are similar because that little tilde represents similar. Let's just go through and understand why these two triangles are similar based off of the characteristics that I have here. Notice that if ratios of corresponding sides are equal, it's important to note what does it mean to be corresponding. If you look at the order of the letters, that is very important when you're setting up these ratios. Notice that AB are the first two letters of this triangle, DE are the first two letters of the second triangle, and notice that I've taken those two sides and created a ratio. I put AB first and DE second. Notice that if I look at the last two letters of the first triangle and the last two letters of the second triangle, they are corresponding. They've created this second ratio. BC is a part of the first triangle. Since AB was a part of the first triangle and I put that on top, I'm putting BC on top as well. If I look at the first and the last letter of the first triangle, as well as the first and the last letter of the second triangle, they create then that third and final side, which gives us our last ratio. Once again, the two letters of the first triangle go on the top. So if I now use my numbers that I have in this diagram, let's show that these are truly then equal. AB is 8. I put that on the top. DE is 4. That goes on the bottom. I always want ratios reduced down to lowest terms. Well, 8 over 4 simplifies to 2 over 1. If I look at BC, that's a length of 10. Looking at EF, that's a length of 5. I can simplify this down. It simplifies down to 2 over 1. If I look at AC, that's 12. If I look at DF, that's 6. Notice how this reduces down to 2 over 1. So I was able to get three ratios that are the exact same. So that indicates that, yes, ratios of corresponding sides are equal in this particular picture. If I need corresponding angles to be congruent, well, looking once again at the picture, A and D, those are marked the same. A and D, they're in the same spot of the triangles. They are corresponding angles, and the diagram is telling us that they are congruent. B and E, same thing. They're marked the same. They're lying in the same spot. When we look at how the triangles are named, those are corresponding angles that are congruent. And then lastly, C and F. They are marked the same in the picture. They are also in the same spot when I'm writing out the names of those similar triangles. Those are corresponding angles that are congruent. So everything checks out in this picture. I have similar triangles because both ratios of corresponding sides are equal and corresponding angles are congruent. So let's use that idea to solve this problem. I'm telling us that we have similar triangles. We want to find x. So before I do anything with that diagram, I'm going to go and look at the letters in this statement. Triangle JKM is similar to triangle NKL. I want to set up corresponding sides, and I want to create ratios with them. So JK, first two letters of the first triangle, I'm going to put that on the top of my ratio. Going over to the second triangle, first two letters are NK. There's my first ratio of corresponding sides. That equals, if I look at the last two letters of the first triangle, that's KM. If I go to the second triangle, last two letters, KL. So that's why I've got this ratio of corresponding sides. Last set of sides, we've got the first and last letter, so JM. Go to the second triangle, first and last letter, NL. So here's my ratio of all corresponding sides. And because I have similar triangles, I know that those ratios are equal. So let's use this information because if my goal is to find x, well, all of these values of x are representing a side. And so that's why I don't really have to focus on what angles are congruent in this. I just need to talk about side lengths here. So notice that x plus 2, that's representing the side of JK. Well, that means we're going to have to use this first ratio because JK is that side in this ratio. If I look at the fact that x plus 7 is representing MK, we'll notice that MK or KM is the second ratio. So I don't really care then about this third ratio. I just need to have two ratios set equal to each other. So we have enough information. Let's plug in what we know. So JK, I said, was x plus 2. That has to be over NK. We'll notice that NK is given to us as a length of 6. Go back to that second ratio, KM. That's x plus 7. That goes over KL. We'll notice that that side's given to us as 8. I'm going to put those binomials in parentheses because now I want to cross multiply and start solving for x. So I know that 8 has to get multiplied by x plus 2. That has to equal 6 getting multiplied by x plus 7. To get rid of those parentheses, I'm going to distribute those numbers. I've got 8x now plus 16 on the left. I have 6x plus 42 on the right. Start solving for x. I'm going to subtract 6x to combine those. That now gives me 2x plus 16 equals 42. So now I'm going to move the numbers by subtracting the 16. That still gives me 2x, but now 42 minus 16 gives us 26. I'll divide both sides by 2. I'll get a value of x then to be 13. That's all this problem is asking for, so I'm done. And that's how we can use similarity to find, in this case, x. We also talked about similarity in terms of shadow problems. So let's review an example of a shadow problem. It states that a 55-foot tower casts a shadow on the ground. So what I'm going to do is I'm going to create a picture of this scenario. I'm going to create a right triangle where we're talking about a 55-foot tower. So towers, we're thinking about, buildings, towers, those are going to be vertical. So that's going to represent the vertical side of this triangle. It says that it casts a shadow on the ground. I don't know the length of that shadow. I'm going to call then shadows, which are on the ground, so it's that horizontal side, I'm going to call that X. I'm going to draw a second right triangle. So basically then I'll have a similar triangle. So these two triangles are similar. It says that a 10-foot tree, so trees, think about how trees grow. They grow up, so that's going to be the vertical side. Cast a shadow 15 feet long. So once again, shadows are always on the ground. So that's going to be that horizontal side. It's asking how long is the shadow. So once again, that's of the tower. So we want to set up a proportion using these corresponding sides. Two different ways to do it, but normally how I like to do it, I like to think about height over shadow. And so that's dealing with one of the triangles. And then I like to set that equal to the height over the shadow of the second triangle. So I want to stay consistent. You could technically do height over height and then shadow over shadow, but you just want to be consistent. Whatever triangle you start with, make sure that you then consistently use that either in the same spot on the top, or if you do height over height, whatever height you started with on the top, you need then the shadow of that height on the top. So just be, like I said, consistent. So I'm going to do 55 over X because that's representing height over shadow of the first triangle. And that's going to equal then 10 over 15 because that's then height over shadow for the second triangle. I'm going to then start cross multiplying. So we've got 10 times X, and that equals 55 times 15 is going to give us 825. I'm going to divide by 10. That'll give us x. Remember, x is representing the length of the shadow. That's what we're trying to find. When I divide, I'm going to get 82.5. This is talking about everything being related to feet. So it is a shadow of 82.5 feet. And that's how we work a shadow problem.